This meeting is being recorded.
This next video will cover information from section 2.9 and 2.10. There's not too much to review from 2.9. We just are reminded that formal charges are important when we draw these resonance structures. We need to indicate those. And oftentimes when we derive these resonance structures, we're going to end up with one or more formal charges in our final resonance structure after we do this arrow pushing, these movement of electrons. So let's take a look here. We have a structure, so this structure is given, and we know that there's a resonance structure that we can create by these two curved arrows here. So we're going to be moving two pairs of electrons. We have this lone pair up here, so that's going to move from the oxygen down to form a double bond here between this carbon and oxygen. And then this double bond over here between the carbon and carbon will start on the double bond and end up over here. So let's take a look at what that would look like. So we have up top the original molecule, and then we have our two curved arrows. So we see now the oxygen has only one lone pair, but three bonds. And this carbon here has a lone pair. So what have we seen in the past? We've seen the fact that oxygen, to be neutral, would have two bonds and two lone pairs. Or we could do a formal charge calculation and say, okay, this oxygen needs 6 valence electrons, it only has 5, so hence the +1 formal charge. Down here, this carbon has, it needs 4 bonds to be neutral, but we see 3 bonds. We see another bond that's not indicated to hydrogen in the bond line structure. We never draw the hydrogen, so it's assumed. And then we have 2 carbon bonds. So what we would have is 4 minus 5 instead of 4 minus 4 valence electrons with 4 bonds. So that's where we get that -1 formal charge on this carbon here. So always indicate formal charges. That brings us to the next section, section 2.10. There's some patterns that we're going to hopefully recognize, and that will tell us that resonance is possible. So we'll read through these quickly, and then we'll take a look at some specific examples. So we have allylic lone pairs, allylic carbocations, a lone pair that is adjacent to a carbocation, a pi bond between two atoms that have different electronegativities. So we're going to see a lot of this, carbon-oxygen. And then we have conjugated pi bonds in a ring. So benzene comes to mind, right? When we talk about conjugated pi bonds, and we'll learn more about what pi bond conjugation is in a much later chapter, but for now, we'll take a look at benzene in particular. So we have these terms, vinyl and allyl. So we have vinylic positions on, would be these carbons here on this double bond. These are called the vinylic positions. And then we have allylic positions, which would be all 4 of these carbons surrounding this double bond. So we have a double bond and then a single bond. This is the allylic position. But on the ends of this double bond, those are the vinyl positions. So when we look for allylic lone pairs, those would be the ones that can be involved in resonance, right? So this lone pair here, we're told, is not allylic. It is not connected to an atom that is next to a double bond. But down here, we see this allylic lone pair on this nitrogen, which could be involved in resonance because it's adjacent to this pi bond. So let's take a look at pattern 1 and some examples of that. So we have all of these lone pairs that are allylic. So we have a double bond next to a single bond, lone pair on the end. Double bond next to single bond, lone pair on the oxygen atom. double bond next to single bond, lone pair. So you can see the pattern, right? Double bond, single bond, lone pair, and like so. So these are all the allylic um, examples with lone pairs. So these can all be involved in resonance, and we can see how these movements can occur. So let's get rid of all these notations up here so we can compare. So this is the before structures, and then we see these red curved arrows down here, which indicate how these electrons can be moved. Right, so after that, we would end up with a single bond over here and a double bond over here, but that lone pair would have moved from this double bond, so we would end up with a lone pair and a -1 charge on this side. So these are the two resonance structures here. And then we would do something similar here, right? We would end up with just one lone pair on that top oxygen. Then we would have a double bond to that carbon down here. And then this double bond, these electrons would move to the end of this carbon. And we have similar movement and these other structures. So these are all delocalization of an allylic lone pair, and they involve two curved arrows in each of these examples. So let's take a look at pattern number 2 here. Oh, I'm sorry, one more slide with pattern 1. So we have our before and afters, right? So this is one of the compounds that I didn't draw over here. So take a look at these. If an allylic atom was neutral, it would become positive, and then whatever atom receives the lone pair, that will become negative. So if we have neutral over here, right, we end up with a positive and negative charge. So charge is retained, if you will. We have 0, and then +1 and -1 are net 0 in the products after the second resonance structure here. So pattern 2, now we have allylic carbocations. So we have an allylic structure. So we have that double bond, single bond pattern, but now we have a positive charge instead of a lone pair. So this first structure here shows the curved arrow moving that double bond over. So no longer do we have a formal charge on the left side, it moves to the right side. In these cases, we only need to use one curved arrow to show resonance structures, unlike the allylic anion or the allylic lone pairs, where we had two curved arrows. Pattern 3 is when we have a lone pair adjacent to a carbocation. So carbocation is here, lone pair is here at the tail of the arrow. The head moves to form this double bond here. And now our oxygen has 3 bonds, 1 lone pair, so we end up with a +1 formal charge. What we see in this top example is something similar. We see movement of a lone pair to form a double bond, but what we had here was a positive charge and a negative charge, so our resonance structure results being neutral. Right, so we had movement of a positive charge in the first example. We retained that formal charge in our resonance structure. And in the top example, we went from a net neutral charge with one positive and one negative charge to being neutral. So that is how the formal charges are effective in both of these examples. They are retained. So our fourth pattern here is when we have a pi bond, so a double bond, the p orbital overlap between two atoms of differing electronegativity. So if we have a covalent, polar covalent bond, for example, between carbon and oxygen, we can move those electrons around. So that's what we see here. Our carbon results in a carbocation, a +1 formal charge, and those electrons move up to become from the double bond in our carbonyl move up to become a lone pair on our oxygen. So our oxygen ends up with a -1 formal charge. So our last pattern where we should recognize that resonance is possible is when we have conjugated pi bonds. So we have these alternating double and single bonds within a ring. So this is benzene again. We'll get to know benzene quite well between organic 1 and organic 2 classes. But what we see here is the two resonance structures of benzene. And remember, we could show distribution of charge. We can also show a resonance hybrid for our benzene here. So we can just draw this circle inside. So you may see something like that as well. Now, this is a summary slide of all the different arrow pushing patterns or resonance patterns that we were asked to recognize earlier. So we have our two arrows in an allylic lone pair. The allylic carbocation only needs one curved arrow. Also, we have the lone pair adjacent to a carbocation has one curved arrow, and the pi bond that's between two electronegativity differing atoms, so carbon and oxygen in this case, one curved arrow. And then our last ring structure has three curved arrows needed. So see if you can take a look at this structure here and figure out if you see any of those resonance patterns and see if you can draw the resonance structure for this molecule. We will continue with section 2.11 next.